It's kind of fun keeping track of it.
Okay. Well, as long as I don't have to keep track of it, because
it's a lot to keep track
I'm pretty sure that's one of those things that falls into the category of I don't give a bleep.
There you go. So speaking of I don't give a bleep, and do you give a bleep? We've changed it. This is a 2017 change. You're going to explain different how did I put it? Scientific concepts.
Scientific concepts is what you said. Or cooking, apparently, is also an option.
But that's just sexism.
You know, me sitting here explaining how to make brownies out of a box. I don't know how that's even remotely interesting, but hey.
It's really, really useful information, though. Everybody should know how to make brownies out of a box.
Yeah, and every freaking brownie box has the instructions on it.
Yeah, but you're so good at it. I mean, you're very precise. Everybody compliments the brownies. I think you just start with a really good mix. Anyway, but we're not going to do the sexist thing and put you in the kitchen.
No.
We're going to talk about science.
We are going to talk about science.
So what I did here, because I see you've got your Keynote open.
Yes.
I'm going to hand you my phone. This is now a remote control for Keynote. So go ahead and just tap the screen to move on to the next slide.
Okay. I didn't know I could do that.
And next time I will help you set it up where you can do it from your phone.
Okay. All right. So we are starting with dark matter because Vera Rubin died recently, and we discussed her last week on the podcast. And she was one of the people who was instrumental in discovering dark matter.
Okay.
Did
I give a bleep?
Probably not, because you're you.
I give a bleep.
Okay, so the definition of dark matter is that it's unidentified matter that's distinct from regular matter, neutrinos, and dark energy.
So wait, what is a neutrino?
Neutrinos are little particles that go through everything, and they're kind of cool.
And what's dark energy?
Dark energy is way more complicated, and that's pretty much its own topic.
Okay, so now we know what we're doing next week.
Yes, I'm explaining dark energy next week, apparently. So dark matter does not interact with or emit electromagnetic radiation, and it's invisible to the entire electromagnetic spectrum. So, it doesn't emit visible light, it doesn't emit X-rays, it doesn't interact with them,
We have no way of perceiving it.
Really, no way of perceiving it visually. At least in terms of electromagnetic radiation.
So how do we know it's there?
Good question. So, it was discovered by astronomers studying orbital velocity curves of galaxies. And the orbital speed of an object in a galaxy depends on the amount of mass between the object and the galactic center. And this is uniform.
The orbital speed of an object in S galaxy depends on the amount of mass between the object and the galactic center.
Yes. So, the orbital speed of our sun is dependent on the distance of our sun from the center of the Milky Way galaxy.
Okay.
Okay?
Yep.
Okay. So, I apologize for the picture. I'm still learning to use Keynote. So
I razzed her appropriately already, but leave a comment.
Does YouTube censor obscene gestures?
I censor obscene gestures. I do moderate the comments, but for spam,
No, I meant if I flip you the bird right now, are you gonna censor that out?
Anyway, I can't tell what we're looking at. What are we looking at? It's
a velocity curve. So what it is
on the left, the vertical axis. What is that? That's velocity.
Yeah, that's velocity.
And what is the horizontal?
The horizontal axis, and let me pull this up on my phone just so I make sure I get the label right. That's distance.
Distance.
Yeah.
And so we have A. Can everybody see A? It's in blue.
Yes, and it's a nice dotted line there.
It's a dotted line in blue. It's a little hard to see. We'll work on this. We're going to improve this as time goes on.
So basically, once all of a galaxy is within an orbit, the velocity should diminish with distance, and that's
A.
A.
So A represents what the thing's supposed to do.
Yeah.
Right? And it, instead of coming up and hanging across, it's just kind of, it goes up and then
it tapers out
tapers
the farther
out
away you get.
and kind of fades out. Yeah.
And so instead, what the astronomers were noticing was that the orbital velocity doesn't drop off until quite a ways past the edge of the visible galaxy.
Which is B.
Which is B.
Now let me make a note. Let's make sure let's keep everything black and white.
Okay.
Because I know there's at least one viewer that's colorblind.
Okay.
So yeah, so we have the B. It comes up. I will cut back to the camera, so it's coming up like this, coming across, right?
Yeah.
And then that's what it's actually doing. What it's supposed to do is come up, taper off, and then go like that.
Right.
It's not doing it, and the spread gets bigger and bigger.
Right.
So what causes the difference?
That would be dark matter. So in 1975, Vera Rubin and Kent Ford announced at an American Astronomical Society meeting the discovery that most stars in spiral galaxies rotate at roughly the same speed. So this implies that galaxy masses grow linearly with radius well beyond the location of most of the stars in the galactic bulge.
They rotate or they rotate?
They rotate with the galaxy.
They go around the galaxy. Okay.
Uh-huh.
And they all, yeah, it's not like it goes much faster towards the middle, which you'd expect it to do.
Right.
Okay.
And they weren't noticing that. They were noticing that it's pretty uniform throughout.
Okay.
So.
Do you know how to go back? There you go. So this implied, what? This implied that the galaxy masses grow linear with radius well beyond the location of most stars.
Yeah.
So the mass continues to grow outside of the galaxy.
Outside of the bulge.
Outside of the part we can see.
No, because a galaxy is made up of. There's the disk, which if you look on it head on, looks like spiral arms.
Right.
This is a spiral galaxy in particular. There's different types of galaxies. And then in the center, if you look at it edge on, there's a bulge where most of the stars are located. And then you've got the arms coming out from there.
Gotcha.
And that look like a disc at that angle.
That makes sense.
Okay.
This is I'm having flashbacks to playing Spore. I loved playing Spore. Spore was a lot of fun.
Whatever helps you relate.
Sure.
So yeah, that's that.
So they grow. Okay.
Do I need to go back?
Yeah, so they grow outside of that bulge.
Yeah. You know.
So you would see the disc, but it's actually a sphere, and you can't really see that. Is that what you're saying? It's like a sphere. If I started.
It actually kind of looks like one of those toys from the 80s that it was like the flat round disc with the ball in the center.
Oh.
That you bounced on. That's kind of what it looks like.
What was that called? Leave me a comment. Let's go down that rabbit hole and leave a comment with the link to the video, to the commercial. I remember those.
That's kind of what a spiral galaxy looks like edge on.
Right.
So you
that's what it looks like, but it's not behaving like it looks.
Yeah, it's not behaving like it looks.
So what does it actually look like if we could visualize whatever dark matter is there? Is it a sphere? It's almost
kind of. It ends up being almost more like you've got the visual disc and then like a halo around it.
How big's the halo?
It depends.
Okay.
Depends on the size of the galaxy.
Got it. All right, what's next?
Okay. So, no.
Yeah, you were there.
Yeah. Okay.
So Rubin's work was initially met with skepticism. How'd they confirm it?
Hold on. So Yeah, it was initially met with skepticism, but it was confirmed, and the study of galaxy clusters has been of particular importance to the dark matter studies.
Right, but that's only if it's only important if it actually is useful.
It is useful. It's highly useful.
Okay. So the importance of galaxy clusters.
Yes, the importance of galaxy clusters. So the mass of galaxy clusters can be determined in 3 different ways. You've got from the scatter of the radial velocities of the galaxies within the clusters, from the X-rays emitted by hot gas in the clusters, and from gravitational lensing. So what gravitational lensing is gravity acts as a lens to bend the light from more distant source. So behind the galaxy.
So of all these 3 different ways, they're all saying, yeah, it's doing the thing, and it all agrees that it's doing the thing.
Yeah, it's basically what it is. You can determine the mass all 3 ways, and so if they all agree,
right,
then you got it.
There's something there.
Yeah.
And so then that basically we assume then that it outweighs visible matter 5-1. Okay, what's next?
And that would be it.
That's it.
That's it.
What do we do with that information?
Well, it's one more piece into how our universe works.
Somebody needs to hack it. It's time to go.
You know, I mean, we can't go out and test dark matter because we can't get to it.
It's only out there on the edges?
No, it's not on the edges.
Everywhere.
It's everywhere, but we can't see it. So we can't exactly go take a sample of this stuff going, hey, let's go test this in the laboratory. You know, we're limited by technology and our ability to go to it.
Okay, so let me ask you this as a final rhetorical thought.
Rhetorical thought, okay.
Once we understand dark matter, does that mean we'll be able to change computing to where a plug-in actually sounds as good as that tape machine behind you? All right, what's next?